Hello everyone, this is S. Roy. Let's start lecture 3 of Haskell module. And as you already know, we are using the textbook 7 Languages in 7 Weeks by Bruce Tate. And I will be using some of the material from this textbook in this lecture. First, let's revisit lecture 1 and lecture 2 very briefly. Haskell is a type system rich language. The type system is very powerful. Haskell does type inferencing, and we'll see Haskell also supports polymorphism in terms of types. Here is one example of using do syntax that can help in doing IO, input output. Try IO function uses do block, and we are printing something, then getting some text from the user's typing using this get line, and then does some work on that input, and we let this function return something, and that works. You can test that. Now little exercise to refresh what we learned before. Fib is one function we wrote which generates Fibonacci series, and then on top of that, if we use other two anonymous functions and they are composed with a dot operator, and this whole thing, this composed one is used by map, and that is applied on the fib, then what will be the output? So let's here assume that fib is the infinite series for the Fibonacci numbers. Say we have defined that infinite series before, and now we are applying these anonymous functions using map on that. Haskell allows virtually processing an infinite series. So which one will be the correct correct output? The correct statement. I'm sorry. And which one, A, B, C, or D, which one is correct statement? And assume that fib is an infinite series of 1, 1, 2, 3, 5. Actually, this is the fib series, and now we are applying these anonymous functions composed using map, and as we know, that will be equivalent to applying the multiplication with 10. So it seems the last one is the correct statement. That will be the output of this line. Now let's take another exercise. Here we have one small list as the input, and then this map similar, and then we have a take4. So it will be which one? 10 multiplied with 110, then 10, 20, 30, then 50, 80, right? And 4 of them will be taken, so A should be the right answer. Now let's define some polymorphic data type. That's very powerful feature of Haskell, and we need to use this keyword data to do that. Now let's take an example first. We are defining a data type called triplet that is associated with generic type A. And what is the definition of that? The definition is trio and then that same type 3 times. That is the definition. Now I guess without an example it's hard to see. So let's take an example, and a is called a type variable which can vary. A can be integer, or a can be character, or any other type. So that is called type variable. Let's see. So on your Haskell console, if you type trio, then these 3 characters, and you ask Haskell what is the type of this whole thing, then Haskell will recognize your defined type triplet is matching with this type, right? Because your definition says trio of same thing 3 times, and that same thing is character here. Trio of same thing 3 times is defined as triplet of that type, right? So Haskell will respond to you that this thing which you want to know the type of is triplet char type. Do you see the power? So just in one line, user defines this new type triplet with a generic type variable, and then Haskell is able to recognize something like this as the user defined type. So maybe let's run this on the console. I guess that is always a better idea. So let's make it clear. GACI is the Haskell console, and let's paste the code. So this is where we are defining this triplet new data type. And then you can have a variable where you say my x is trio, then a, then b, then whatever, say 4. So these are 3 characters after trio. Now you want to know what is the type of x, and Haskell says x type is triplet of characters, right? And as another example, if you say y is trio, then 34, 4, and 100, so 3 integers I have given, and Haskell accepts that. And then if you ask what is the type of y, Haskell will say that, hey, in a, let's call a as num type, then your data, whatever you give to Haskell, is of type triplet number. A is number type, so triplet number. See the power? Okay, let's come back. Now the next topic is how to define recursive type, which is even more powerful one. And one good recursive data type example is tree, right? Generic tree, like binary tree is one type of tree, but we are talking about a generic tree, can be ternary tree and so on. So here we are defining this new data type tree, which is associated with the generic type variable. And then what is the definition of that? The definition is tree can be subtrees where each subtree is one tree. So this is a list of trees, and we are calling that list of trees as subtrees. So that can be one case, one option for tree. So that is one case definition for tree. And the another possibility for tree is it is a leaf, and of course associated with the same type variable. Now if you are curious what is the meaning of deriving show, that just means this new type which we are defining here, we'll be able to print that type information via Haskell program. So deriving show just adds the printing capability to that type. Okay, so basically show is also a type which can do the printing operation, and we are deriving that. That means we are adding that capability. Okay, now let's define a variable called leaf, and let's call it leaf1, so that matches with this case, right? So according to our previous definition, Haskell should now recognize this as a tree, right? Make sense? And not only that, if you then ask Haskell, hey, what is leaf? Haskell will give you this green response that leaf, small leaf, is nothing but this big leaf one. And for terminology, this term tree, which appears just after the keyword data, that is called that is called the type constructor. Okay, so tree is called type constructor, and the other terms like subtrees, leaf, which are appearing here, those are called data constructors. Okay, and see that a data constructor leaf can hold a value with the type. Now that means that say we have already defined this small leaf, and then on Haskell console, say we are trying to extract this value part which is inside this leaf, then you can write this leaf value on Haskell console, this thing equal leaf, and then using pattern matching, Haskell can recognize that the value is 1. So if you then type value on the console, Haskell will give you this green response. Okay, more examples how to use this recursive type. Let's define bunch of trees. Say tree 1, which has 2 leaves, and that definition can be subtrees where the first subtree is leaf 2, the second subtree is leaf 3, because this is a list of subtrees, right? Let's define another tree, tree 2, and that may look like this. So that is, and the tree 2 is nothing but bunch of subtrees. The first subtree is leaf 1, and then we have another whole subtree here. And how to define that subtree? It's recursively. So here this part will be similar to what we had before, right? So that means something like this, and you see that is appearing here. Make sense? So that is how tree 2 we can define. And if you ask Haskell what is tree 2, Haskell will print you this green stuff. Okay, now let's try to write some utility function on this sort of new recursive data types which we have just defined. The first utility function we will discuss is how to compute depth of a tree. So in this example, this tree has a bunch of subtrees, subtree 1, 2, and up to n. Now if we say already know the subtree 1's depth is d1, subtree 2's depth is d2, and so on. So if we already have those information, then how to get the depth of the whole tree? We have to calculate the maximum of those n subtrees depth, right? And then plus 1, because this given tree has all the subtrees, so whatever was the maximum subtrees depth, we have to add another plus 1 to get this whole tree's depth, right? And for best case, when the whole tree is nothing but a leaf, we can define that depth as just 1, right? So you see that we have to write a recursive function to get the implementation of depth, and this is one way of writing it. So depth function, when input is a leaf, that's the best case of the tree, then we can just return 1. Otherwise, when the tree has bunch of subtrees and the list of subtrees is C, then what we have to do, we can use map and apply the depth function on each item of C. That means each subtree in the list C, we can apply this depth function using map. So that will give us, in this part, will give us the list of all depths like D1, D2, D3, as we have seen in the previous slide, like here, right? So that will be returned by this map depth C, and then take the maximum of that and plus 1, and that should work, right? Okay. Now in addition to depth, maybe another good utility function to write is how to compute the total number of leaves in the tree, and let's call it numLeaves. That is also a recursive function. So when the tree has just 1 leaf, doesn't matter what is the value in the leaf, because we are just trying to calculate how many leaves are there, which has nothing to do with the value. That's why it's wildcard. So numLeaves of a leaf is just 1, because there is only 1 leaf. Otherwise, when there is a subtree, that means a list of subtrees, which we are calling C, then the number of, total number of leaves will be sum of each of those subtrees number of leaves, right? So if we can apply this numLeaves function using map on each item on the subtree list, so then we'll get for the first subtree how many leaves are there, for the second subtree how many leaves are there, and so on. And then we are going to just sum them up to get the total answer, right? It's really cool. You can see that. Now so far in our discussion, we only focused on leaves. We did not consider any inner node in the tree. But in some application it may be necessary to consider inner nodes. So here there is a tree where leaves are square nodes and inner nodes are circle. So the first question is how we can extend the previous tree type to include this inner node in the tree type. That is very simple. So when we are talking about subtrees, then not only just say what is the list for the subtrees, also add another A that stands for that inner node. Okay, so maybe it's a good idea for me to define a tree with inner node on Haskell console, and that will give us a better idea. So maybe first, that is not good, let me clear it, and maybe let's open the file and let's check whether maybe those can work, because I guess this is the same thing, right? So tree, subtrees, and leaf, and here tree, subtree, and leaf, right? So to save our time we can reuse this, and maybe we don't need this. So here we are defining a tree. Now again, what is this data type? So we have the definition of tree here, which is subtrees, and there is an inner node and then the list of subtrees. Another possibility is just leaf, right? So here we have defined one tree whose inner node is 3 and there are then 2 leaves, correct? Now if you want to say check whether this works, then let's run it, which is this, and then we had that tree defined and it seems that works, correct? So that tree is nothing but what we have seen there. Okay, so now let's go back and let's see how the new definition of depth on this new tree type will work. Now fortunately we see it's very similar to the previous depth version. So depth on leaf, that means when the tree has only one leaf, it's still 1. Otherwise, when the tree has subtrees with an inner node and then list of subtrees, then get the maximum depth of all the subtrees like before and then just add 1. So it seems the depth function is exactly same as before. This inner node has no special influence on that, right? Now let's talk about the other function, which is number of nodes on this newly defined tree type. So number of nodes on the first case, when there is only one leaf, it's still 1. And the other case, when there is subtree list C and inner node X, the number of nodes should be the sum of the number of nodes in each of those subtrees, like what we had before. But don't forget to add 1, and that is coming because of this inner node X, correct? So maybe it's a good idea to copy this piece of code and go there, and then again maybe we can go back to our file and we can add this function definition num nodes, right? And then we can save that, and then let's test what is tree is that, and what is num of nodes on this tree. So we should apply that function on this tree, and that should return 3, right? Because this is one node, leaf 2 is one node, leaf 4 is one node. Let's see whether it returns 3. Yes. So that means that works, correct?